This paper explores the effects of non-inertial frames on quantum entanglement, particularly in the context of Rindler coordinates. The study examines how quantum states transform between Minkowski and Rindler bases using Bogoliubov transformations. A key focus is the entanglement degradation observed in accelerating reference frames analyzed through Perez partial transpose criterion. The role of Dirac fields and their resilience to entanglement degradation compared to bosonic fields is also highlighted. To further understand these effects, the study delves into how Minkowski single particle states relate to Rindler modes through Bogoliubov transformations. The properties of quantum fields in accelerating frames are examined with an emphasis on the distinction between bosonic and fermionic field entanglement. A crucial aspect of this discussion is the role of spinorial affine connections in defining how Dirac fields behave under transformations. Additionally, the analysis highlights how adjusting the locus of the peak in wave packets influences entanglement behavior, providing insight into how quantum correlations shift in non-inertial frames. Building on these foundations, the discussion moves to how entanglement is affected by uniform acceleration, particularly through the Unruh effect. The study investigates how quantum vacuum states and excited states transform in Rindler space, demonstrating that entanglement degradation depends on the structure of the Hilbert space. The Perez partial transpose criterion is applied to examine separability conditions, revealing notable differences between bosonic and Dirac fields in their response to acceleration. Notably, Dirac fields exhibit greater resilience to entanglement degradation, suggesting fundamental differences in how quantum correlations behave across the different types of fields. A deeper exploration into mode expansions of quantum field follows, illustrating how field operators decompose into different frequency modes in accelerating frames. By utilizing Rindler coordinates, the study reveals how these expansions influence quantum correlations, directly impacting entanglement properties. The authors employ Parseval's theorem to quantify entanglement distribution, while also discussing the role of Grassmann scalars in fermionic fields behavior. The finding underscored the importance of Hilbert space structure in shaping the evolution of entanglement under acceleration. Bringing these elements together, the study confirms that entanglement degradation is an inherent feature of acceleration, with Dirac fields and demonstrating greater resilience compared to bosonic fields. The role of spinorial affine connections and Bogoliubov transformations is emphasized in understanding quantum correlations in accelerating frames. These insights hold significant implications for quantum information theory in relativistic settings, pointing towards potential experimental applications and deeper theoretical models in future research.